When the first data packets rolled in from Webb's Deep Field Survey this month, nobody thought anything unusual was coming. It was supposed to be routine, just a follow-up look at a dim, early universe galaxy logged months ago. But the moment the team ran the spectral analysis, the whole room shifted. Conversations died mid-sentence. People leaned in toward their monitors. Something was off. The readings didn't match anything in the archives. They were too sharp, too bright, too tightly packed for an object that small. And sitting dead center in the data was the last thing anyone expected to find this early in the universe's timeline. The unmistakable signature of a supermassive black hole, one weighing in at nearly 400 million suns. For a moment, the whole room froze, not because anyone doubted the numbers, but because everyone knew they were real. This wasn't some blazing quasar lighting up the ultraviolet spectrum. It wasn't a wild, fast-feeding black hole tearing through space. It was something far stranger. A quiet, fully formed gravitational giant, massive, mature, and completely out of place in such a young universe. The cosmic timestamp put the universe at barely 500 million years old when this light began its journey. And by every model we've built, a black hole this huge shouldn't exist yet. That was the problem, and everyone in the room knew it. This discovery, hidden in what should have been just another routine spectrographic reading, ignited NASA almost instantly. Word jumped from team to team, then spilled into partner labs across Europe and Asia, and the same line kept showing up in every internal email. This is way too big for the timeline. The early universe wasn't supposed to look like this. It should have been messy, uneven, slow to build. Tiny proto-galaxies flickering out, early stars collapsing, matter gathering in scattered clumps. But inside this one ordinary-looking object, Webb had picked up signs of something impossible, a powerhouse that, by all logic, should have taken billions of years of mergers, collapses, and cosmic construction to assemble. And yet, there it was, complete, quiet, waiting. To really feel how shocking this is, you need a quick refresher on how black holes normally grow. The small ones, born from collapsing stars, start out tiny by cosmic standards, maybe a few dozen times the mass of our Sun. From there, they bulk up the slow way, merging with other black holes or gradually feeding on surrounding gas. But that growth is glacial. Even in perfect conditions, it takes billions of years for a black hole to climb past a few million solar masses. Webb's target wasn't a few million, it was pushing 500 million. That raised the one question every scientist was thinking: how? When Webb zoomed in on the region, the mystery only deepened. Everything looked calm. Suspiciously calm. The galaxy hosting it was tiny, dim, almost unnaturally compact. No wild starbursts, no chaotic structures, none of the hallmarks of a young galaxy still being built. Something didn't add up. There were no signs of tidal distortion, nothing to suggest a recent galaxy merger. But the biggest shock? It wasn't bright. A black hole this massive, if it were feeding, should outshine its entire galaxy. The swirling gas around it should blaze like a cosmic lighthouse. Instead, this thing was practically invisible. Its existence showed up only through the way it tugged on nearby stars and the faint, almost ghost-like distortions in their velocity patterns. That left just one conclusion. This black hole wasn't feeding. It was asleep. And a dormant supermassive black hole this early in the universe is far stranger than an active one. Active black holes announce themselves. They flare, they launch jets, they light up the sky. Dormant ones vanish into the background. They swallow light instead of producing it. Spotting one this size takes absurd precision. And right now, there's only one instrument sensitive enough to detect something this subtle from over 13 billion light-years away. Webb. Once the initial shock wore off, the real work kicked in. Teams across the world dove into the data, trying to unravel how this black hole could have bulked up so insanely fast. One theory on the table was direct collapse, the idea that a huge cloud of pristine, early universe gas could skip star formation entirely and fall straight into a black hole. But even the boldest models only predicted masses around 100,000 solar masses, maybe a million if you stretch it. Webb's black hole blew past those limits by hundreds of times. Another possibility? Enormous star clusters forming all at once and collapsing under their own weight. But every simulation hits the same walls. Radiation pressure pushes outward, gas gets blown apart, and gravity just can't haul material in fast enough. The early universe doesn't build giants like this, not at this speed, not at this scale. And yet, it existed. A silent, undeniable reminder that something in the early cosmos moved far faster than we thought possible. Harvard astrophysicist Dr. Priya Das didn't sugarcoat it during the briefing. We're not looking at an error. We're looking at a formation pathway that shouldn't exist. Other researchers tried to stay cautious. Maybe the black hole wasn't truly dormant. Maybe it had gone through a violent feeding phase earlier and then settled down. Maybe we'd simply caught it during a rare moment of calm. But that theory only made the mystery deeper. For a black hole to quiet down, it has to run out of nearby fuel. It has to clear, consume, or blast away the gas around it. And doing that requires an entire galaxy's worth of material funneling inward first. That takes time. A lot of time. Far more time than the early universe ever had. With every new measurement, the tension between what we were seeing and what physics says should happen kept tightening. The accretion disk was barely glowing. The stars nearby showed extreme gravitational bending, and the center behaved like a single, impossibly dense point. Test after test came back with the same verdict. The black hole was real. From there, the theory started branching out. Some scientists floated the idea of a cosmic jumpstart, regions of the early universe where matter might have been far denser than we assumed, letting it clump together at breakneck speed. Others pushed even farther, suggesting strange behavior in dark matter itself. Maybe early dark matter halos collapsed much faster, dragging gas down into deep gravitational wells long before normal astrophysics could slow things down. Whatever the explanation was, it pointed to one conclusion. Something in the early universe was playing by rules we don't yet understand. Some researchers even wondered, could this black hole have formed before its galaxy, pulling the stars and gas in afterward? It's still speculative, but with each of Webb's discoveries defying our early universe expectations, that scenario is starting to feel a little more plausible. Then there's an even wilder idea. Teams studying the cosmic microwave background, the faint afterglow of the Big Bang, proposed that some black holes might have formed in the first seconds of the universe itself. These primordial black holes are still hypothetical, but the concept is simple and staggering. The universe might have produced these cosmic giants almost instantly, before galaxies even had a chance to exist. In a universe racing outward at unimaginable speed, there might be pockets of matter collapsing far faster than our equations allow, creating massive black holes almost instantly. Until now, these ideas were mostly theoretical, the kind of math exercises that never touched reality. Webb's discovery changed all that. As the data spread, NASA called in observatories across Europe and Japan to verify the find. The verdict was unanimous. This object matched a massive, dormant black hole. Questions poured in. Reporters asked, why was it asleep? Why so enormous? Why so ancient? But the scientists had an even bigger question. What does this do to our understanding of the universe's timeline? If a single 400 million solar mass black hole can exist this early, then maybe there are countless others, lurking, silent, and waiting to rewrite everything we thought we knew about cosmic history. Maybe entire populations of black holes formed long before galaxies even matured. Maybe galaxies didn't give birth to black holes. Maybe they grew around them. This flips the cosmic playbook entirely. Instead of galaxies spawning supermassive black holes, perhaps galaxies were shaped, steered, and accelerated by the gravitational giants at their cores. Some theories have even hinted at this. Black holes as seeds for galaxies to form around. But in those models, the seeds are tiny, slowly growing over billions of years. Webb's discovery? It's like stumbling upon a fully grown tree in a forest of newborn saplings, already massive, already dominant, and completely rewriting our understanding of the early universe. As these ideas spread, the mood in NASA meetings changed. This wasn't just another early galaxy, it was a direct challenge to the opening chapters of cosmology. What else had the universe pulled off in its first moments? What else had formed faster than anyone thought possible? Behind the scenes, scientists scrambled to model the black hole. They ran simulations with different chemical mixes, gas densities, and temperature profiles. They even tinkered with the distribution of early dark matter. Nothing could explain a dormant giant like this, unless they invoked exotic formation scenarios that haven't been confirmed. And yet, the evidence didn't lie. The gravitational signature was unmistakable. The mass estimates, even on the low side, were staggering. The universe had just handed them a mystery bigger than anyone expected, and it was real. As Webb kept collecting spectra from the galaxy, another striking pattern emerged. The stars around the black hole weren't scattered or chaotic. They moved like those in mature galaxies. They weren't random. They were orbiting a central, massive, silent anchor. The heart of this galaxy was already settled. But why? That question stretched beyond physics into philosophy. What does it mean when the universe breaks its own timeline? When objects form faster than the equations say they should? When a cosmic giant sleeps in the early dark? To the public, the story might be simple. Webb has found another early black hole. But for scientists, it's far more than a headline. It's a challenge, a puzzle, and a glimpse at a universe that refuses to follow the rules we thought it did. It's a signpost, a hint that the early universe was far more dynamic, aggressive, and efficient than our models ever predicted. And the most unsettling part? The black hole is dormant. Not dangerous, mature. Something this massive shouldn't have had time to settle down, and yet it has. Silent, impossibly large, already fully grown while the universe was still in its infancy. As scientists gear up for the next round of Webb observations, the stakes are clear. If more dormant, supermassive black holes show up at similar redshifts, cosmology won't just face questions, it will enter a new era. Not one of panic, but of revelation. A timeline rewritten. A universe more active in its earliest moments than we ever imagined. Whatever comes next, one thing is certain. Webb is forcing the cosmos to reveal secrets it's held since the dawn of time. And this silent, ancient, 400 million solar mass giant is just the beginning. Hit like and stay tuned.